two-dimensional magnetism has become very hot in the last few years. But actually, it's not unfair to say that it's kind of old story at least in the time scale of our microscopic understanding of magnetic properties, which has been indeed renewed in the last 4 years. So we shouldn't forget that our microscopic understanding of magnetism was made possible only after the introduction of quantum mechanics. And the most important contribution came from during the 30s by many of the fathers of quantum mechanics, just to mention Stoner or Heisenberg, or even before Van Vleck. And it's already in 1944 that Onsager proposed an exact solution for the two-dimensional Ising model, showing that in 2 dimensions, this model could sustain a long-range ferromagnetic order. Now, at that time, this contribution from Onsager was already recognized as a very important one in the field of statistical mechanics, but somehow in the community of physicists doing magnetism, it was considered such more like a kind of mathematical exercise, because the model was considered too simple to describe real magnetic properties, for which the appropriate model already at that time was considered to be, at least in localized magnets, the Eigenberg model. Anyhow, one had to wait 20 years more or less before the Mermin and Wagner, developing on the work that Pierre Eigenberg was doing on the long-range order in two-dimensional superfluids and superconductors, proposed a theorem which showed that no long-range order could be established in 2 dimensions. Nevertheless, a couple of years later, and thanks to the advances in neutron scattering technologies, it was possible so experimentalists were able to observe and to characterize a kind of quasi-2-dimensional order in bulk system. The prototypical system is shown here as this 3-dimensional structure, where basically magnetic ordering could, long-range magnetic order established only along the layers containing the magnetic nickel ions. And this started a field of, let's say, 2D magnetism, so quasi-dimensional magnetism in bulk systems, that has been very active, especially during the 90s, because of its close connection with the parent compounds of high TC superconducting cuprates. And some years later, this first observation, another subfield of, let's call it dimensional magnetism, started when the intrinsic magnetic properties of monolayer thick metallic films grown on substrate that was started to be observed and characterized. So by the end of the 20th century, we had these 2 kind of very active and big fields, which are more or less connected to the field of 2-dimensional magnetism. But the real revolution, of course, came in 2004, when it was so the freestanding graphene monolayer was realized for the first time. And let me also mention that also the freestanding graphene was kind of unexpected because of the Peyer's and Landau prediction that such really 2-dimensional systems should not exist in reality. And after that, indeed, many other 2-dimensional complementary materials to graphene have been realized and studied and characterized, just to mention the transition metal dechalcogenides that have been discussed so far yesterday. Anyhow, even though there have been some attempts to include magnetic properties, to engineer magnetic properties into graphene, we had to wait another 10 years, more or less, before the magnetic properties of truly 2-dimensional materials was reported. And this was a breakthrough in the field, because there is a conceptual difference in this case, because we are dealing now not with 2-dimensional magnetism, but with 2-dimensional magnetic materials. And we have seen already yesterday that the prototypical example of such materials are this chromium-based triiodide and this telluride, which are both semiconducting van der Waals crystals. In the bulk form, they are both ferromagnetic with critical temperature of about 60, 70 Kelvin. In both cases, they were able to show, especially for the chromium III iodide, that this could maintain a relatively high critical temperature, even in the monolayer limit. And this was explained in terms actually of easing ferromagnetism. The situation is a bit different in CGT because at least in this original paper, actually they claim that this system should obey a truly Eigenberg model. But anyhow, they could really measure the effect of the dimensionality reduction, the critical temperature, pointing to an intrinsic two-dimensional ferromagnetic properties. And from 2017 to now, a bunch of other materials have been reported. Here I just provide the 3 examples. These actually show some important differences with respect to these chromium-based systems, in the fact that all these materials are conducting systems, are metallic, so the magnetic properties are itinerant in character, and probably because of this, they have a much higher critical temperature that can also be easily tuned by electrostatic doping. And of course, the excitement about this system is, from my point of view, twofold. From one side, it's from theoreticians, it's an ideal platform to study both magnetic and spectronic concepts in the truly two-dimensional limits, meaning a truly isolated two-dimensional system. But also, from the application point of view, there is not only the advantage of dealing with a really nanostructured system, but also the possibility to tune much more efficiently the properties, in this case magnetic properties, by applying electric field or electrostatic doping or even mechanical strain. Now, when we talk about two-dimensional magnetism, of course, we have to face the Mermin-Wagner theorem that I just quoted before. So I reported here, I quoted exactly the words of the abstract of the original paper because it contains all the information one needs. So we are starting by looking at the Eigenberg model, which is defined here. The Eigenberg model is extremely simple. We have already seen in the previous talk. Basically, that describes the exchange interaction between pairs of spins of localized magnetic moments. The coupling is just a scalar. And typically, it's assumed to be relatively short range. So the typical model assumes just the first, second, and third next nearest neighbor. And the point is that this model is isotropic. What does it mean? That it's rotational invariant, because this the energy described by this Hamiltonian just depends on the relative orientation of the magnetic moments. And of course, that means that it underlies a continuous symmetry, which is SO3 in case of classical spins, or SU2 in the case of quantum. And the point is that if we assume that this magnetic system establishes a long-range order, this long-range order breaks this continuous symmetry. And this has two consequences. The first is that actually we have an infinite number of distinguishable states which are obtained by any arbitrary rotation of the magnetization axis here, which are degenerate. And the other thing that comes simply from the fact that we are breaking a continuous symmetry, that we expect to have a gapless spin excitations. Now, the point is that what is the physical content of the Mermin-Wagner theorem is that if we assume that we have some finite magnetization at the finite temperature, we can express this as the sum of the ground state magnetization and the effect of the thermal fluctuation of the system. The point is that we can ask ourselves, is these thermal fluctuations may be so strong that they can destroy the magnetic order? And we can, so I'm not providing here the proof of the original proof of Mermin-Wagner theorem, but just to let you understand what is the point. So we can write down this, the contribution of the thermal fluctuations, like this integral containing the density of states of the excitations of the system multiplied by the probability, the thermal occupations. And of course, what is crucial here is that the density of states depends on the dimensionality of the system, and also on the interaction range. And basically, if you assume that the excitation spectra can be written like this power law with a power of n, then it's easy to show that the density of states actually scales with this power law with the power of dimensionality minus n divided by n. And for ferromagnetic spin waves, one immediately realized that this density of states become a constant, and then by expanding the Bose-Einstein probability function, one sees that this the thermal fluctuations show a logarithmic divergence at any finite temperature. That basically means that such spin wave excitations are so easy to excite in 2 dimensions that they immediately destroy the long range order. Now let's review for a second what are the assumptions behind the theorem. So, okay, first of all, we are looking just at the role of thermal fluctuations. So the Mermin-Wagner theorem doesn't tell anything about the ground state at t equals 0, even though in that case one should include also quantum fluctuations. The second important assumption is the one of short-range interactions. So in principle, the original proof does not apply to itinerant ferromagnets, even though quite recently it has been the proof has been extended also to include the system. So it may not be enough to have long-range interaction to guarantee a 2-dimensional long-range magnetic order. But the crucial assumption is the one of isotropic interactions. And it is relatively easy to understand this because the presence of an arbitrarily small anisotropy basically gap the excitation spectrum. And the presence of a gap in the excitation spectrum means that basically one can remove the logarithmic divergence by introducing a low energy cutoff in the integral that I shown before. And this was, for instance, realized by Bander and Mills in the late 80s when discussing exactly the thin ferromagnetic films, where they show that indeed the long range ferromagnetic order could be allowed in the presence of an arbitrarily small uniaxial anisotropy. But of course, then the critical temperature was importantly renormalized in the 2-dimensional limit. Of course, this also allowed to reconcile the Eigenberg and the Ising picture. This is also kind of trivial now because we can simply look at the Ising model as the limit of a Heisenberg model with an infinitely large uniaxial anisotropy. Let me also mention that during the 80s, another possible mechanism has been proposed to cause long-range order in low dimension. It was proposed originally by Jacques Villain, and it's called the order by disorder mechanism, and is strongly related, of course, to the presence of frustration, which in some cases it's enough to reduce the symmetry from the continuous one to a semi-continuous or discrete symmetry. Now, having understand that the isotropy assumption is the most important one, we can wonder which are the mechanisms responsible for anisotropy. And the most ubiquitous one, we have already seen also in the previous talk, is the dipole-dipole interaction. This is, of course, depends on the relative orientation of the spins. It can be immediately seen if we consider a collinear phase, and we take as the magnetization axis the bonding vector axis between the two magnetic moments. And of course, this interaction select a specific direction for the magnetization, which depends on the relative orientation of the magnetic moments, as it's seen here for the ferromagnetic and antiferromagnetic cases. And a related mechanism that also has been touched upon in the previous talk is the shape anisotropy, which is basically related to the effect of the demagnetizing field arising at the surface of the sample. But it's important to notice that this dipole-dipole interaction, even though it's in principle should imply that any magnetic system has a low temperature long range order, even in 2 dimensions, has an energy scale which is very, very small. It's of the order of millikelvin. So it's 3 to 4 order of magnitude smaller than exchange interaction. So that means that one could theoretically have a transition, but it's a ridiculously small critical temperature. A much more effective mechanism is the single ion anisotropy. This has a relativistic origin. It's a perturbative explicit expression it's very simple, it's shown here. And it's, of course, a tensor that comes from the fact that we have in this perturbative expansion the matrix elements of the orbital angular momentum. And typically, this can be expressed by diagonalizing the tensor in the basis of the principal axis. And this is the formulation that is most often encountered in terms of longitudinal and transverse components. And what I plot here are 3 simple examples of the potential surfaces that are induced by the single ion anisotropy. And of course, when we have a negative longitudinal component, the minimum of the energy, of course, for spins aligned along the z direction. So this is an easy axis single ion anisotropy. In the opposite limit, we would have an easy plane where spins can freely rotate in the xy plane. So we still have a kind of continuous symmetry in this case. The more general case, we have a more complex form of the potential surfaces where some specific directions show a saddle point in the potential surface. Now, the point is that spin-orbit coupling is also responsible for the anisotropy of the exchange. And this also was realized by Moria in the 60s, where basically he included the spin-orbit coupling in the super exchange perturbative derivation of the exchange coupling. And of course, due to the presence of the spin-orbit coupling, the scalar exchange in coupling constant must be transformed into a tensor. Now, a tensor can be always decomposed in these 3 terms. First one is simply the trace of the tensor, which is isotropic. And then we have these 2 combinations. One is the antisymmetric and the other one is the symmetric combination that is taken to be traceless in order to have this isotropic term here. And this corresponds exactly to the standard Eigenberg isotropic model. The antisymmetric part actually corresponds to the Jaruzelski-Moria interaction. Moria, when he derived this expression from the general superexchange theory, actually started from this antisymmetric decomposition and then rewrite this in the form that has been proposed a couple of years before by Jaruzelski. And these 2 terms are typically taken into account when discussing exotic magnetism. And then, in principle, we should also have this anisotropic exchange term, which is also called the 2-ion anisotropy, for a reason that will be clear in a second. Now, let's have a more detailed look in these new terms. So the Jaruzelski-Moria interaction also can be derived as for the Anderson superexchange part of the Heisenberg interaction. And the difference here is that instead of having just one virtual intermediate state where we have one electron that jumps from one side to the other side with opposite spin and then jumps back, we have the possibility of having a mixing mediated by the spin-orbit coupling between the states of one of the 2 sites. And as also the previous speaker was mentioning, there are very strong symmetry constraints on that. And in particular, I'm talking here about the atomistic Jaruzelski-Moria vector. The point is that if the bond has an inversion center, then this Jaruzelski-Moria vector must be equal to 0. This is really related to the bond. So in principle, one could have a centrosymmetric system where locally the local bonds do not have an inversion symmetry. So you can have locally the Jaruzelski-Moria vector and globally no Jaruzelski vector. But now we can perform a similar perturbative expansion And finally, that actually also we have this anisotropic exchange tensor. You see that it's very similar to the expression of the Dzieloditsky-Moria vector. The only thing is that here we have an additional virtual intermediate state where basically we allow the spin orbit, the atomic spin orbit coupling to mix states on both sides of the system. So we can conclude here saying that both the Dzieloditsky-Moria and the anisotropic exchange are driven by the atomic spin orbit coupling. And the reason why this anisotropic exchange is usually neglected is because it scales as the atomic spin orbit coupling constant to the square. We can also have a look at the competition between these terms. So we know that the Heisenberg interaction would favor collinear spin phase, so spins align parallel or anti-parallel depending on the sign of the interaction, but does not provide any information on the direction, the global direction of this collinear phase. The Dzieloditsky-Moria interaction instead would favor perpendicular configuration of the spins, but not only that, it also has two other important effects. One is that it selects the rotational plane where the two spins count one to respect to the other, and also the endness of the angle between the two spins. This is simply related to the axial character of the vector product between the spins. Instead, the anisotropic exchange displays a behavior which is much more similar to the dipole-dipole interaction. So it tends to form collinear spin phases aligned along preferential directions, which are nothing else than the principal axis of the tensor. Now, from here, we immediately see that we have two kinds of competitions. So there is an energy competition between the Heisenberg and Dzieloditsky-Moria interaction, which would promote some noncollinear phase. And also we have a competition between the preferential directions selected by the anisotropic exchange and the Dzieloditsky-Moria vector, because also this interaction try to select an oriented surface where the spins want to count. And this naturally brings me to the other aspect that I wanted to introduce, that is the magnetic frustration. So we have also here two general kinds of magnetic frustration that we can consider. So now I'm just looking at systems with isotropic Heisenberg interaction. We can imagine to place them on some geometrically frustrated lattice. So the simplest example is a triangle with antiferromagnetic coupling. So clearly we can immediately place two antiparallel spins on one bond, which would be happy from the point of view of the interaction, but we don't know how to place the third spin. This is particularly evident in the case of Ising spins, because they can just point up or down. So we cannot find a situation where all the bonds are happy with the energy cost due to the antiferromagnetic interaction. In the case of Heisenberg spins, instead, spins can rotate in order to minimize the energy due to the antiferromagnetic interaction. And typically you find this 120-degree configuration. We have two isoenergetic configuration, which differs only on the handedness of the rotation. So they basically have opposite chirality, but are still degenerate in terms of energy. And there are a lot of examples of geometrically frustrated lattice. So of course, we can have a triangular lattice. Also, the Kagome lattice has a similar kind of frustration. And here I also show the 3D example of a similar frustrated lattice, which is the pyrochlore lattice, where you see you have sites sitting at the vertex of a tetrahedron, which of course have triangular faces. One can also have frustration emerging just from competing exchange interactions in a system, in a lattice which is not frustrated. So the simplest example is just a spin chain with competing ferromagnetic and antiferromagnetic interaction. And of course, here we would have pairs that are happy because of the ferromagnetic coupling, but then the second nearest neighbor spins would not be happy because they need to pay some antiferromagnetic energy here. And then depending on the ratio between the two competing interactions, we can have some exotic spin configuration. So for instance, if we have again just Ising spins with these competing interactions, when the antiferromagnetic second nearest neighbor interaction is larger than half of the ferromagnetic one can stabilize this peculiar up-up, down-down phase, which, by the way, breaks the inversion symmetry of the lattice. And this has been proposed, for instance, in the beginning of the multiferroic field. Now, if we have instead the Eigenberg spins, we have a similar thing. So we can break the collinear phase that one would expect by simply isotropic non-competing interaction, stabilizing then a magnetic spiral, again above a certain threshold for the ratio between the two competing interactions. And let me stress the fact that, of course, as we have seen before, the Dziarowski-Moria interaction is also responsible for such non-collinear coplanar phases. And what the main difference with so there are two differences mostly when comparing spirals induced by competing exchange interaction and competing Heisenberg-Dziarowski-Moria. So the first is that in the presence of competing isotropic interaction, there is a threshold value. So one needs to have a strong frustration in order to induce a transition from the collinear phase to the non-collinear phase. Whereas in the case of the Dziarowski-Moria interaction, in principle, an arbitrary small value of D would establish an helical phase. And the only thing is that, of course, the periodicity of such a spiral phase would be inversely proportional to the value of the Dziarowski vector. But there is another important difference. So if we now assume to apply a reflection across a mirror plane, which is perpendicular to the screen and parallel to this line, what we would end up is we would end up in two spirals with the opposite handedness. So in this upper case, spins are rotating clockwise, and these lower panels, they're rotating counterclockwise. Now, for the case of competing isotropic interactions, these two magnetic spirals are completely degenerate in energy, whereas these two are not, because the presence of the Dziarowski-Moria interaction removes the chiral degeneracy, and this is why it is called a chiral interaction. Now we can also have another class of frustrations, which is not related now to the competition between of exchange interactions. This also has been proposed by Moria a couple of months before the publication of his famous paper on the Dziarowski-Moria interaction. And he proposed this mechanism trying to explain the weak ferromagnetism, so a non-collinear phase in an antiferromagnet, which is nickel dichloride. And so in this system, the structure is relatively simple, is shown here. The main ingredients are the fact that the interaction are mostly isotropic antiferromagnetic. There is no Dziarowski-Moria interaction. Now the point is that there are two magnetic sublattices with perpendicular single ion isotropy axis. And this, of course, brings in a competition again, because now, because of this perpendicular easy axis, the spins also want to be perpendicular one to the other, and this competes with the isotropic exchange that wants them to be parallel. So in the end, the ground state or the long range order in this system is a canted antiferromagnet, where the two magnetic sublattices starts from being completely antiparallel, and then in order to optimize the magnetic anisotropy energy, they cant a bit. And so this is a non-collinear phase induced by the frustration of an isotropy, but it's not chiral. Now, one may wonder if it's possible to have instead a kind of removal of chiral degeneracy with this kind of mechanism. And I would say that yes, this is possible. That depends if in some particular cases. So here I show the expected, well, at least the modeled early magnetic phase of a rather complicated system, which is this oxide with a langasite structure. And I will not enter in detail in too many details here, but basically this has been proven experimentally that there are helical chains in this structure whose chirality is fixed to the structural chirality through the frustration of the single ion anisotropy in this triangular plaquette, which forms the chains. And also in this case, in principle, one would also have the Dirichlet-Moirier interaction, but the Dirichlet-Moirier interaction could not explain the presence of an elliptic deformation of the helical modulation along the chain, which is instead naturally explained in terms of this frustrated single ion anisotropy. Okay, now we have all the ingredients to discuss our quest for exotic two-dimensional magnetism. So we have seen that, okay, we need an isotropy to have long-range order in low dimension. This is typically always guaranteed. The main problem is related to the scale of the transition temperature. And the other thing is that we can use frustration or several kinds of frustrations to induce non-collinearity and helical magnetism, even though up to now, generally, the chiral magnetism is provided only by antisymmetric Dirichlet-Moirier interaction. So luckily, we have a wide class of layered materials where we can look for magnetic properties, which is basically the magnetic counterpart of the TMD class that we have seen yesterday. And these are van der Waals transition metal dihalides or trialides. And of course, the Chromium I3 iodine is belonging to this class. There are several similarities between these two classes of materials. So I'm showing here the two typical structures of an individual layer of the van der Waals system. So in the case of trialides, we have seen that we have this hexagonal lattice, which is formed by transition metal in an octahedral environment with edge sharing octahedra. The dihalides case is pretty similar. The only difference is that we are filling the whole of this hexagonal lattice and obtaining a triangular lattice. But for the rest, they also are formed by edge sharing octahedra within each layer. We focused on a specific subclass of this material, which are the nickel-based. This because of this class of van der Waals magnetic materials has been known since the 50s. And here is shown the bulk structure. In the bulk, they have a relatively low critical temperature below the 100 Kelvin, but this is typical of this class of material. But what is most interesting that nickel dichloride is the only collinear magnetic phase in the bulk system, while the bromine and iodine counterpart of this subclass of materials, both were reported to display a very complex and magnetic phase. Here I report the experimentally found propagation vectors for the spiral phases, and you see that basically they have a very strong out-of-plane component, but also an important in-plane component. So these spirals are going across the layers, and from the neutron scattering measurements, the experimentalists deduced that they should be proper skew spirals. So instead of looking at the bulk, we wanted to study the two-dimensional magnetism. So we focused on just the monolayer. As I said before, the monolayer is formed by is a triangular lattice of edge sharing octahedra. There is small trigonal compression along the direction perpendicular to the layer. In the case of nickel, we can predict what is the size of the local magnetic moments by considering the electronic filling. So we have to host 8 electrons in the D shell of the nickel in the presence of a trigonally distorted octahedral field. And basically, you see from this scheme that we would have 2 unpaired electrons in the 2-fold generative G levels that would correspond to a high spin configuration with S equal to 1. And this is confirmed by our DFT calculations, where we find that magnetic moments locally are more or less slightly smaller than 2 Bohr magnetons. The other interesting thing is that we are increasing the halogen, the size of the halogen ions, at least the size, the extension, spatial extension of the p orbitals of this ligand. And in fact, by increasing this, we see that there is an induced moment also on the halogen ions when going from the chlorine to iodine case. And I also remember that here, so the spin-orbit coupling of the nickel is the same, of course, while the spin-orbit coupling of the halogen is increasing along when going down the column. Okay, so the first thing we did was to estimate the isotropic exchange coupling constant. And basically, we see consistent trends in the three materials we considered. There is a very strong ferromagnetic nearest neighbor interaction, as in the Chromium I3 iodine system. We find a negligible second nearest neighbor interaction, whereas what was kind of surprising for us at the beginning was that we found a very strong antiferromagnetic third nearest neighbor interaction, which was strength increases by increasing the ligand, the size of the ligand. And from here, so we would expect, so we have here two things. We have a geometrically frustrated lattice, the triangular lattice, and a very strong competition between antiferromagnetic and ferromagnetic interaction. So one would expect non-collinearity, a non-collinear solution for this system. This can be immediately seen by considering mean field energy for this lattice with this interaction. And in fact, what we would expect from this mean field analysis is that, again, there is a threshold value for the third nearest neighbor antiferromagnetic interaction, which is absolutely well fulfilled both in the bromine and in iodine case. Now, this is just for from the isotropic interaction. So we know that there are many degeneracies here, of course. So the one is the refraction, let's say, of the rotational invariance of the starting model. So we can have all classes of coplanar helices in the system, which are all degenerate. So we can have the proper skew, where the spins rotate in a plane which is perpendicular to the propagation direction. And also we can have an infinite number of cycloids, where the spins rotate in a plane which contains this propagation vector. And of course, we can think of rotating this rotational plane around the propagation direction, and we'll still have the same energy. There is another class of degeneracy, which comes from the discrete threefold symmetry of the triangular lattice, and that implies that we have three equivalent propagation directions for these spirals. But we still have to go further to introduce anisotropic terms in the system. So we include the spin-orbit coupling in our calculations, and we evaluate the full exchange tensor alongside the single ion anisotropy. And the first thing to notice here is that because of the edge sharing of the octahedra in the structure, each nickel-nickel bond is heterosymmetric. So it has an inversion center, so there is no Dziarowski-Moria interaction in the system. And in fact, from our calculated exchange tensor, we find that the exchange tensor is symmetric. The second thing is that increasing, so going down in the column of halogen atoms, we move from a situation the chlorine case, where basically there is no anisotropy, at least in our numerical accuracy, we couldn't find any anisotropic term in the exchange, nor in the single ion anisotropy. But already in the bromine case, we start to see a non-negligible anisotropy in the exchange, while there is no single ion anisotropy. And finally, in the iodine case, the effect is really, really strong. So we have much stronger anisotropic exchange than single ion anisotropy. That in this case would be an easy plane one. So this is a positive term. So there is an important role here of the atomic spin-orbit coupling of the ligand, not of the transition metal. And so, okay, what are the consequences of this anisotropic term? So to understand this, we performed classical Monte Carlo simulation, feeding the model parameter extracted from ab initio. So we focus first on the nickel dibromide case. This is from our calculation, there is no single ion anisotropy, but the presence of the exchange anisotropy enables a transition, which we estimated to be around 20 Kelvin, to a spiral phase, which is called here a single Q phase, because I told you there are three possible solutions for the Q. And here, what I've shown here, this is a snapshot of the spin texture at low temperature taken from the Monte Carlo simulations. And the color scale is the component perpendicular to the plane. And what you see from here, this is basically, it looks like a proper screw. So where the spins, so the spiral modulation is parallel to the x direction, and spins rotate in the plane perpendicular to it. But actually, we also found that there is a small cycloidal component that emerges from by decomposing the spin structure factor by these peaks appearing in the spins in the x component of the spin structure factor. And this suggests that the presence of the exchange anisotropy, it's not trivial, so it's introducing some no coplanarity also in the system. Now the no coplanarity effect is even more evident in the case of nickel iodine. So here again, I'm showing the spin structure factor. And you see here there are 6 peaks. These 6 peaks, so each pair of peaks correspond to a single Q spiral. And this is a realization of a triple Q state, which can be thought as a superposition of the 3 spirals, but all simultaneously. The point is that if you look at now at the snapshot of the spin texture at low temperature, we have this very exotic lattice, where you can see that there are strong cores with the magnetic moments pointing perpendicular to the lattice layer, which is a contradiction with the fact that we predicted for this system an easy plane single ion anisotropy. Even more interesting, we see that the in-plane component of the spin texture is very unusual. And actually one can identify these 3 axes around which basically the handedness of the in-plane component change sign. And now, okay, we have, thanks to the previous speaker, we know that this is suggesting that actually we have skyrmions in the system. So we have seen that there are a lot of different types of skyrmions. And what I wanted to show here is that the spin texture of this Q equal 2 anti-skyrmion. So this is like the Q equal 1 anti-skyrmion, but it's characterized by the fact that it's multi-chiral. So that there is a change of chirality of the handedness of the in-plane texture when moving around this high symmetry direction. And this looks very similar to what we found in our simulations. And the idea is basically, so what we have is we can imagine to start from an isolated anti-skyrmion, put it on a triangular lattice, and then start to squeeze the lattice until in the end we end up with a spin texture which is very reminiscent to the one we found in our Monte Carlo simulation. Of course, we can provide a better characterization of such topological phase. And the thing is that to evaluate the topological charge in the discrete model that we are using instead, so we cannot use this the well-known analytical expression, continuous expression that is given here on the left. What we can do is to evaluate this topological charge by summing the solid angle formed by triplet of spins on each angle of plaquette, which is basically determined by the so-called scalar spin chirality, which appears here in the numerator. Now, so we calculate this quantity in our simulations, and what we found is that indeed, in the corresponding to the spontaneous transition that we observed previously from the specific heat, we also have a diverging behavior of the susceptibility associated with the topological charge, and that the topological charge tends to an integer number, which here is 6, simply because it's the topological charge of a magnetic unit cell. So the basic periodic unit of our magnetic structure, which is shown here by this this rhombus here, and that you see that it contains actually 3 cores. So we are really looking at a anti-Skyrmion lattice. Even more interesting is now, so the point is that this is a spontaneous transition. So there is no magnetic field in the model, and there is no Jaroditsky-Moria interaction. So the only anisotropic terms here are the single ion anisotropy and the easy plane single ion anisotropy and the exchange anisotropy. Even more interesting, if you apply now a magnetic field, what we see at some point there is a field-induced transition. Here again, I plot the spin structure factor, but you see that there is an additional peak at the gamma point. That simply means that there is a net ferromagnetic moment in the system, which is induced by the applied magnetic field. And the thing is that now the lattice is formed by a different topological object, which is nothing else than a Skyrmion, a Q=1 Skyrmion. So basically, we have also a sequence of field-induced topological transitions in the system, where we can use the field to go from a anti-B Skyrmion to a Skyrmion, then eventually to a trivial ferromagnetic phase. Now we can wonder what is the role of the anisotropic exchange in this particularly exotic magnetic phase. And the point is that, okay, to understand that, it's better to visualize what are the principal axes of the anisotropic exchange. And basically, we found that there are 2 almost degenerate eigenvalues corresponding to principal axis, which lies in the plane of the plaquette formed by the nickel-iodine atoms. And then there is, which are for magnetic in sign, so they are negative. And then there is the third positive eigenvalues correspond instead to a principal axis, which is perpendicular to the plaquette. The point is that these plaquettes are not parallel, not coplanar to the lattice layer. So basically, you can see it both from the top view here, where this plus and minus corresponds to iodine atoms above or below the lattice layer, or from this side view. So these are canted, this principal axis. They are canted, they are pointing all in different directions. So this is similar to the anisotropy frustration that I shown you before for the single ion anisotropy, but it's of course on the 2-side anisotropy term. And now we can compare the direction of this principal axis for the exchange anisotropy with the in-plane spin texture of the spins. And you see that there is a one-to-one correspondence. So this is so basically we can think of this triple Q state as a superposition of a spiral, which is actually stabilized by the presence of this anisotropic exchange, which as a plus also provides a well-defined in-plane texture of the spins. The other interesting thing is that this is related to the fact that this frustrated anisotropy occurs on a triangular lattice. Basically, when we have this triple Q state, this anisotropic exchange frustrations actually acts as an emergent chiral interaction. What does it mean? That we can compare the energies of chiral partners of the same structures, for instance, for this anti-B skyrmion with opposite chiralities. And if we look at the energy contribution of the different terms, they basically, of course, have the same energy contribution coming from the isotropic interaction, but what makes them different is exactly this two-state anisotropy, so that removes the chiral degeneracy between these two states. So basically, okay, so we can also compare with the Chromium I3. As I said before, the main difference between the Chromium I3 and the nickel I2 is the lattice. So we have an hexagonal lattice as opposed to the triangular lattice here, and also we have a different exchange path for the third nearest neighbor interaction, and as a consequence, the magnetic frustration it's much smaller. However, the anisotropic exchange has been also calculated relatively recently, and in that case, also Chromium I3 has an important anisotropic exchange contribution, which actually is of the same order of the single ion anisotropy. So it also contributes to the magnetic anisotropy of the system. Of course, the smaller frustration of the system is responsible for the fact that in Chromium I3 we have at the end an effective easing for magnet with a ferromagnetic ground state, whereas in the nickel diiodine, the interplay of the strong magnetic frustration of this large frustrated exchange anisotropy drives to the spontaneous formation of a Skyrmion lattice. Okay, so I think I can conclude. So basically, what is really crucial is the combination of frustration and anisotropy that may drive to an exotic form of two-dimensional magnetism, especially. So what is interesting in this case is basically we are considering a system which has no Dirac-Moore interaction, and it is the frustration of an isotropic exchange that may act, even though locally it's not a chiral interaction. When placed on a geometrically frustrated lattice in combination with strong magnetic frustration, it can drive, it can form a chiral magnetic configuration. There are a lot of open questions and issues. So one thing, for instance, is to understand the origin of such a large anisotropic exchange in nickel iodine, and to see if is it common to other systems also, not only iodine. And for this, it's important probably to take into account the role of the atomic spin-orbit coupling of the ligand. The other thing that could be interesting to check in this kind of systems is to explore the possibility to tune the Dirac-Moore interaction. That in the pristine monolayer it's absent because of symmetry, but one can think of breaking such symmetry in some way by applying electric field, or even more interesting, probably by applying strain in nanotubes, so curving the monolayer to induce, so to remove the symmetry constraint of the Dirac-Moore interaction that could be probably even larger than the anisotropic exchange. And then the last but not least very interesting point to me is to understand and to explore the possibility of having magnetoelectric coupling in such kind of systems, and possibly multiferricity, which is often found in systems with helical magnetism inside. By the way, the bulk nickel diiodine was shown some years ago to be multiferroic. So the question is it possible to have a two-dimensional multiferroic in this class of system? That would be very interesting to know. And then let me conclude just by thanking the modern group at the CNR unit of Chieti, especially Danila Amoroso and Silvia Picozzi, who contributed to this work. And then, okay, acknowledgement to the funding, and thank you all for your attention.
Thank you very much, Paolo, for this very interesting, very detailed talk on these new materials or novel magnetism. I don't know if these materials were known before, but it seems that their magnetic properties are only now discovered, being discovered. It is certainly very exotic, as you indicated in the beginning. So we have now the discussion session. Normally, we should have a break of perhaps 10 minutes, but we